Okay, so let's get going today. We do have a bit of stuff to cover. So the outline for this week, well, see how far we get today, and the final quiz 3 on Friday. I may not be able to cover all of this, but we'll finish up the period finding algorithm, and then I want to talk about entanglement. This is a topic that is very deep, but we can't cover all of that. But we'll try to explain some of the curious features of quantum mechanics, specifically entanglement, which powers a lot of, we think, is one of the reasons it has so much power over classical computers. So, and I'll go through a few of these topics as time permits. This is just a repetition of last week's announcement. Just to remind you, we have the quiz 3 this week on Friday. We have the teaching survey available. I've already mentioned how much we would appreciate your feedback. And also the project report and code assignments are due next week. The rubrics have been put up, and I still haven't heard from, I think, one group about project titles. So you need to let me know soon. Okay, so modular exponentiation, just to recall, it's an arithmetic operation, really, where we just take the power of a number and then modulo another number, modulo meaning find the remainder after division by that number. And so as you can see here, 2 to the 0, which is 1, modulo 7 will give you 1. 2 to the 1, modulo 7 will give you 2. 2 squared, mod 7 is 4, etc. If you keep going, we see that the pattern 1, 2, 4, 1, 2, 4 keeps repeating. And the length of that repeating sequence is called R, and it's called the period. Or another way to define it is that it's the smallest positive number such that a to the R modulo n equals 1 modulo n. And we can always find such an R if a and n are coprimes, which is, we also saw this here, 2 to the 3, modulo 7 is 1 mod 7, so the period is R is equal to 3, which is also the same as the length of that repeating sequence 1, 2, 4. So all of those are equivalent to finding this period. Okay, this problem is also, as I said, called period finding or order finding. Now, why do we care? It's one of those interesting operations in which it's easy to find the that, or to verify that R is the period, because all you have to do is find a to the R modulo n. So for example, 2 to the 3 modulo 7, you can immediately verify that's 1, right? But if I ask you find the period of that sequence, well, beyond small numbers like 2 and 3, etc., it starts to become very difficult. So like we did one example last class, where we took 91 to the power 43 modulo 131, and you saw already just finding out what that was, finding out the value of that was already kind of, it required some work. And then if you want to find the period of that sequence, then you have to try a lot of numbers before you get the period. So that's why it's hard. But once you know the period, you can immediately verify, or once you're given a guess for the period, you can immediately verify it, whether it is a right or wrong answer immediately. So this is another example of those one-way type functions, where it's, once you have an answer or a guess at an answer, which is reasonably good, you can verify it very quickly. But going the other way, when you don't know anything about the problem, it's very hard to solve it. And that's why it's at the heart of many cryptographic protocols. Okay, so our quantum solution, we just started on this last class. So first of all, we assume we have a gate that performs modular multiplication. We already saw how to do that by hand in the last class, but so you can implement it as a quantum circuit. And once you can implement it by a classical circuit, once you can implement it as a classical circuit, we just make it reversible by the usual tricks that we have talked about in this class. So our gate U performs the modular multiplication A y modulo n. So what it means is if I apply U to say the state 1 here is of course just the bit string 0, 0, 0, 0 up to 1, right? And again, y is a bit string, which is restricted to n bits, and therefore can go from 0 up to capital N minus 1. Capital N is 2 to the power n. Okay, so this is u0, 1 modulo n is just a to the 0 modulo n. And then we can take the first power, that gives me a to the power 1 modulo n. Second power, a squared modulo n. And then the nth power, the rth power of u will be a to the r modulo n, but as I just said, that is equal to 1 modulo n, because r is the period of this exponent, the modular exponent. Okay, so our quantum solution to find this r will go in 3 steps. Okay, in step 1, we'll construct an eigenvector Vs of u, and we will show that its eigenvalue equals this value over here. Our next step will be to apply phase estimation. Remember, phase estimation allows us to get an approximation to the eigenvalue. Okay, it gives you an m bit approximation to the eigenvalue s over r. The eigenvalue here, I mean, e to the 2 pi is obviously just constants. So really what we are looking for is some estimate of s divided by r. And the phase estimation circuit gives us an m bit approximation to that eigenvalue s over r. Okay. And so we need to apply phase estimation. And in the phase estimation procedure, which I'll show you in a couple slides, we need to construct 2 things. One is the controlled U gates, and the other is the eigenvector Vs. We have to prepare this eigenvector Vs. So we need to know how to do that in this particular quantum circuit. And finally, of course, even after finding S divided by R, we still need to find R at the end. So we may have S divided by R to m bits, but S, remember, is one of the eigenvalues. So we need a way to go from S divided by R to R itself. Okay. All right. So, but I'll just go step by step. So these are the 3 steps. We want to tackle each step at a time. Okay. Is the steps clear to everyone why we're doing this? Okay. Hopefully it'll become more clear as we go along. Okay. We first need to construct the eigenvector. By construct, I just mean write down that what this eigenvector is. We still need to then prepare it in the quantum circuit. But I'll show you that's possible once we understand what the eigenvector must look like. Okay. So my claim is that the eigenvector that we need for u is this series over here, which is I take a to the 0 modulo n and I multiply it by e to the minus 2 pi s times 0, which is that's e to the 0, which is 1. Okay. The next one is e to the minus 2 pi s times 1 divided by r, which is e to the minus 2 pi s by r. The next one will be e to the minus 2 pi I 2s divided by r, 3s divided by r, up to e to the minus 2 pi s r minus 1 divided by r. Okay. Remember, a to the r modulo n will again be 1 modulo n. So we don't include that in the series because that's already included over here at the beginning. Okay. We just need to go to a to the r minus 1, just over here. Okay. That's the claim. And I can write that as using the summation symbol that I'm sure you're all familiar with. It's just e to the minus 2 pi I s k divided by r. K goes from 0 up to r minus 1. And this is the series over here. Okay, so first let's prove that this is indeed an eigenvector. So the eigenvector I've written down is summation k equal to 0, 1 over r minus 1. That's our Vs. And the claim is that this is an eigenvector, that is, it satisfies u times Vs equals 2 pi I s over r times Vs. That's our claim. Okay, this is what we have to verify, basically. So to verify it, well, first of all, I remind you, which I just wrote down on the previous slide, but it's just basically I'm repeating that u acting on each of these states. This is, of course, the state just 1, because this is 1 modulo n is 1. So that is just 0, 0, 0 up to 1. And that, according to that earlier definition of u, gives me a to the 1 modulo n. U squared acting on 1 is equal to a squared modulo n up to u to the power, sorry, I guess I didn't need. Okay. So u squared acting on 1 is equal to u acting on this a modulo m. Okay. So which is equal to a squared modulo n. So as you can see, every time I go up by 1 power, I am just equivalently writing. So u acting on a to the r minus 1 modulo n by a chain of reasoning is just u times a to the r minus 2 modulo n, etc., etc. And so we just get finally a to the r modulo n. You can see that the action of u on any one of these is to add 1 to this power. A to the r minus 1 becomes a to the r modulo n, but a to the r modulo n, because r is the period of this sequence, is simply equal to 1 modulo n, which is again the state 1. So this is nothing but just restating the definition of u. The u is defined to be this particular gate. Okay. All right. So if it is given to be this gate, now I take u and I operate it on the state Vs. Okay. And that is just 1 over root r times summation k equal to 0 r minus 1 times e to the minus 2 pi I sk divided by r times u acting on a to the k modulo n. Okay. So u acts on each of these states, and since its basic effect is to add a power of a, so that becomes a k plus 1 modulo n, and everything else here remains the same. Okay. So given this expression, what I can do is I can write let k plus 1 equal to n, some new number, and then this whole summation can be rewritten as 1 over square root of r, m equal to 1 up to r, e to the minus I, 2 pi I, s, and then wherever k is there, I need to put in m minus 1 divided by r. And then this a to the k plus 1 becomes a to the m modulo n. So from this, we can take out this e to the minus 2 pi s times minus 1. That's just e to the 2 pi I s divided by r. So that part comes out. And then I'm left with 1 over square root of r, summation m equal to 1 up to r, e to the minus 2 pi I s m divided by r times a to the m modulo n. Okay. If I write out this summation, you'll see that it's exactly equal to Vs. So if I write out the summation and compare it term by term, you'll see that this is simply Vs. So therefore, we have proven this result. So I'll just show you that in a second. So, but basically the result is already done over here. This whole thing over here is in fact Vs. Therefore, we have just shown that u acting on Vs gives me e to the 2 pi I s over r divided times the ket Vs. So now I just want to look at that summation. So let's write out all the terms in the summation, and you'll see that it's exactly equal to that earlier summation that we wrote. So the first term in the summation is m equal to 1. Okay. So that's e to the minus 2 pi I s divided by r times a modulo n plus e to the minus 2 pi I s times 2 divided by r, a squared modulo n, and so on and so forth, until we get to the last term over here, where we substitute m equal to r. So that's e to the minus 2 pi I s times R divided by R times A to the R modulo N. Well, as you can see, this term over here is e to the minus 2 pi I s, right? Where s is some integer. Therefore, this whole term is 1. Okay, so this part is 1. And this part over here, a to the r modulo n, is simply 1 modulo n, because r is the period of the of this sequence. And therefore, this is exactly equal, if you look here, to this same series over here, because it's simply taking, if I just move this last term up to the first term, then that's state 1 plus e to the minus 2 pi I s over r plus e to the minus 2 pi s times 2 over r. And of course, here, if I want, I can write e to the minus 2 pi I s r minus 1 by r. A r minus 1 modulo n. That term must also be in the series. And that will now become the last term in the series, which is exactly equal to this expression over here. And therefore, the two series are identical term by term. Okay, so that is the proof. So U is indeed an eigen, the state Vs is indeed an eigenstate of Vs is indeed an eigenstate of U with the eigenvector 2 pi I s divided by r. Okay. Yeah, and here's that series again. You can see it here again. So it's e to the minus I 2 pi s 0, which is just 1, times a to the 0, which is 1, modulo n. That is the last term in that other series that I had on the board. So everything is identical in these two series. Okay, so that's our result. So we have completed step 1. We have shown that Vs is indeed an eigenvector of U with the eigenvalue over here that I claim, that is 2 pi I s divided by r is the eigenvalue. Okay, our next step is to construct the control U gates. Well, the control UX gates, again, since U itself is a classical circuit, we can simply say that we will apply it to any other input state by multiplying, by taking the modular multiplication that we have already shown how to do for any one particular state. It'll take n squared number of gates, depending on how many bits you have, but it's a polynomial function of the number of gates. Okay. So we simply because in the phase estimation, which I'll show you the circuit, let me just show you that circuit here. This is the circuit for phase estimation. The circuit for phase estimation requires these control U squared, control U4, control U to the 2m minus 1 gates. That's what we're trying to do here in constructing these gates. Okay. So we already saw the classical algorithm, for example, repeated squaring, which takes order, n cubed number of gates. So we can easily then construct easily, meaning it's possible. I'm not saying it's easy, but it's possible to construct the classical circuit and make it reversible. Okay? Once we have a classical circuit or algorithm, we can make it reversible. Okay. All right. Now quantum solution step 2b here, was to prepare the eigenvector Vs. We have to actually do it in a circuit. How do we do that? Okay. And my claim here is that I can prepare not just one Vs, that is one of the Vs, but I can prepare all of them in a uniform superposition of the eigenvectors by simply applying an X gate to the rightmost qubit. So very simple preparation step. I take the rightmost qubit, I apply an X gate, thereby creating the state 0, 0, 0, 0 up to 1, right? So 0, 0, 0 with the last bit turned into 1. And my claim is that this state is the uniform superposition of all the eigenvectors. Vs, not just any one of them, but all of them. Okay, so that's very nice. So let's make sure that that's right. what is the uniform superposition of all the eigenvectors? It is this summation over all S equal to 0 up to R minus 1, because right, S is again restricted to be between 0 to R minus 1, because it's one of the periods, so we can't have anything greater than that period. So times PS. Okay. So these are all the possible eigen states and their superposition that I'm writing here. Well, I just start by substituting for Vs. That is that other summation that I had just erased. This summation k equal to 0 up to R minus 1 e to the minus 2 pi I sk divided by R a to the k modulo 10. Okay, now I can interchange this summation and this summation order. So I write this as 1 over square root of R, summation k equal to 0, R minus 1, 1. Let's just write this as 1 over R. 1 over square root of R, that's just a constant. Sorry, 1 over R there. And then I get this term in here. S equal to 0 time to the R minus 1. What I'll show you is that this thing here is just a number, right? Because it's a summation, or you can think of it as an integral or a number, basically, because it's a series which is running over this S, right? And the K is fixed because the K is outside the series. So K for any given K, this series will be e to the minus 2 pi I S going from 0 to R minus 1. So it will be e to the minus 2 pi I K over R plus e to the minus, 1, of course, S equal to 0 will be 1. So if I want to write this out, this will be 1 plus e to the minus 2 pi I K by R plus e to the minus 2 pi I 2k divided by R, etc., up to R minus 1. So that's the series in here, in this summation. So all I have to do, and that's exactly what I'll show you here, is to understand what the series does for different values of k. Okay? And I'll show you that for k not equal to 0, for k equal to 0, that series over here, this series, let's call it some series, let's call it capital S. Okay. So for k equal to 0, I'll show you that S equal to R. Okay. And for k not equal to 0, S will be equal to 0. Okay. So it's a very simple series in that sense. It sums to R for k equal to 0, and for k not equal to 0, it sums to 0. Okay, so for k equal to 0, this summation is very easy to see that it's indeed exactly what I just said, because it's summation k equal to k S equal to 0 up to R minus 1, and then e to the minus 2 pi I sk divided by R, but now I've set k equal to 0 here, so this is just summation S equal to 0 up to R minus 1 of 1. Because when k equal to 0, this exponential is just simply the number 1. And therefore, this is just 1 summed from 0 up to R minus 1, so that is R. Okay, so we have proven the first part. And now the second part, we look at this, and actually I kind of wrote it here. You see that this is 1 plus some complex number. If I call this number, whatever it is, let's call it X. Okay, this is or Z, right? This is a complex number Z. Okay, and then that's Z squared and Z cubed up to Z R minus 1. Okay. Okay, so for k not equal to 0, if I set Z equal to e to the minus 2 pi I k divided by R, that's our series, that's our term Z over there. Then this summation, this S is equal to 1 plus z squared up to z to the r minus 1. Okay, this is a geometric series. You can do the geometric series calculation any number of ways. I'll just skip straight to the answer, which is that this is e to the minus z to the r divided by 1 minus z. Okay. If you're not sure how, just multiply this series by z and then subtract, and you'll see the solution come up. Okay. Anyway, okay. So that is 1 minus z to the r, which is, if I substitute now for z as e to the minus 2 pi I k over r, I get e to the minus I 2 pi and z to the r, and so this is k over r, so this is k over r times r. Okay, so r and r cancel, so I'm left with e to the minus 2 pi I k, and then down here I'm left with e to the minus 2 pi I k divided by. Okay, so this is 1 minus e to the minus 2 pi I k. Remember, k is an integer, okay, and whatever it is down here, e to the minus 2 pi I k over r, it doesn't matter because this e to the 2 pi I k is an integer. For an integer value of k, this value is 1. So 1 minus 1, this is 0. Okay, so therefore we have shown that this with this result over here, as I promised, that S is equal to R for k equal to 0, and therefore the only term in this summation that survives is the k equal to 0 term. All the other terms are 0 because this coefficient here goes to 0 for all the other terms. Okay, so if this summation, if the coefficient is 1 for is R for k equal to 0, that is 1 over r times that first term, which is a to the 0 modulo n. As you can see, 1 over r times r, so that cancels, and we are simply left with the state 1. Okay, which of course can be prepared by simply taking the bit string 0, 0, 0 up to 0 and applying an X gate to the rightmost qubit to produce the state 1, 0, 0, 0 up to 1. Okay? So that is the proposed approach to preparing this uniform superposition of all the eigenstates. And that's why it works. That this is indeed true. Any questions on this proof? It's a lot of math, I know, but we had to show it so that you understand why it works. Okay, so we have solved step B, 2B, sorry. And now I want to ask you a question. Okay. Suppose that I told you that there are only two eigenvectors, V1 and V2. Okay. And I prepared an equal superposition of them. Okay. And then I applied the phase estimation circuit, which is over here. Okay. So imagine that the input here was a superposition of V1 and V2, not just V1 or V2, but it was V1 plus V2. And I apply the phase estimation circuit. And at the end, I measure the eigenvalue register. Okay. What will I get? What will happen at the output? If I prepare an equal superposition at the input of V1 and V2, then what will happen at the output after the phase estimation circuit is applied to it? What answers can I get? Yes?
When you get an answer that is the superposition of like the two, so like you get an answer for V1 and
yes.
you get an answer for V2, the answer for V1 plus V2 would get superposition of the two answers.
Well, would it be a superposition because I measure at the end?
Oh, no. Well, if before you measure, it would be superposition
right.
of the two answers, but after it collapses.
It collapses. Very good. And so what will I get at the answer? Output will be either?
Yeah, it would be either one or the other.
Exactly. Either one or the other. And then the output on this side will be either one of the eigenvalues or the other of the eigenvalues with equal probability. So we see in this particular approach to the order finding, I have to try the algorithm multiple times because I prepared an equal superposition of all the eigenvectors. Okay. So when I run the algorithm, I'll get one of the answers at the end when I collapse it. Correct? I won't get all of them at the same time, or I'm not guaranteed to get the right answer, so to speak, right away. Because I can get any one of the eigenstates, VS, at the end. Okay, because I prepared a uniform superposition to begin with. So at first, this may seem a bit, so for 2, it's okay. I just run the algorithm twice and I have a chance, if I run it enough times, for sure, I'll get all the possibilities, V1 or V2 will surely show up on the output. And remember, in the end, we want that eigenvalue, right? That eigenvalue is what we care about, which will be on this register over here, the eigenvalue register will have the eigenvalue over here. And that's what we really care about, okay? The eigenstate also, but it's not as important to us. We really care about the eigenvalue because that is what gives us the guess at the R, the period, okay? So let's go through it. Suppose that is the question. So suppose I prepare at this point the equal probability superposition, then we're going to get one of the VS after measurement and one of the eigenvalues, the corresponding eigenvalue, which is S over R. And again, this I can interpret as some register, Lm-1 up to Lm-2 up to L1, L0. So M bits, basically. That's what I get at the end. Okay. So, but just remember that there's a probability I may not get the right answer, so to speak. Okay, but at any given step, I'm going to get one of the eigenvalues. Okay, after measurement. Okay, but now that I have the eigenvalue S over R to M bits of precision, I still need to find R itself. Okay, so that is a further algorithm, but luckily it's a completely classical arithmetical algorithm that I'll explain in this. It's called the method of continued fractions. So I'm not going to go into, you don't need to know it too well, but I think it's pretty neat. So I'll just show it to you in a quick sketch. Okay, so suppose we get this particular bit string. So I chose like 5 bits over here, 1, 2, 3, 4, 5. Okay, and let's say I got one of these as the answer, okay, with some probability, right? Okay, then and I convert that from binary into a regular decimal number, which is 0.1562, which I can just get by taking 1 divided by 2 to the 8 plus 1 divided by 2 to the 32. Okay, that's what this is. So that is this 0.1562. So we can write 0.1562 in decimal as 1562 divided by 10,000. Straightforward. I write that as 0 plus 1 over 10,000 by 1562. Again, completely allowable. And now I divide out 10,000 by 1562. I get a quotient of 6 and a remainder of 628. Okay. So these first two numbers, 0 and 6, are part of my continued fraction expansion of this number 0.1562. I can keep going. Okay, so I start with that earlier 0 and 6 and this remainder over here, 628. I invert that remainder again. Okay, so I write 628 by 1562 as 1 over 1562 by 628. Again, I apply division and remainder. So I get a quotient of 2 and a remainder of 306. Again, as you can imagine, I invert that and I keep going. I'll skip some of the remaining steps and give you the final answer, which is this over here. And at the final step, you notice we get a remainder of 1 and a quotient and this quotient 8. Okay, so we'll keep this last quotient 8 because now the remainder is 1. We can't go any further. We can't, inverting this will not give us anything more. So therefore, we stop here. This is the final continued fraction expansion of the number 0.1562. And these values 0, 6, 2, 2, 19, and 8 represent the continued fraction expansion of the number 0.1562. Okay. So I did it by hand here, but you can, you can either use something like Mathematica, which has already got it built in, or you can write your own function in Python. Hopefully you can see this is what's called a recursive function. Basically, you do one operation, and then you keep doing it again and again until you reach some end condition. Okay. Okay, so in our example above, this was a continued fraction. So now we need to use this to get an estimate for that S over R. From that, we need to use it to get R itself. Okay. And oh, by the way, these things are called convergents. Just a terminology. So for example, the 0th convergent is just this first number. So that would be an approximation to our S over R. The next one is 0, 6. So that would be the first convergent, which is 1 over 6. The second convergent would be 0, 6, 2, which would be 2 over 13, etc., etc. So we can keep going this way. We can get, the third convergent is 5 over 32, etc. And we can approximate the number 0.1532 by these convergence. Okay. So now you may wonder what this has to do with our problem. Our problem was we need to determine from S over R the value R. And we recall that S must be between 0 and R minus 1, and R must be lesser than capital N. Remember, the problem we are trying to solve is finding the modulo N, which is N here is 7, right? In our example that we just worked out earlier. Okay. So our question is, can we find R, which is less than 7, such that it approximates this S over R in our answer from the quantum computer? Okay. And indeed we can. So the best approximation to S over R, such that R lesser than N equal to 7, is that S equal to 1, R equal to 6 back here. So you see here that this is the only one that fits the requirement that S must be lesser than R and R must be lesser than 7. Okay. So therefore, we now need to check that 3 to the 6 modulo 7, is that really the right period? Okay, and it turns out it is. So if you calculate 3 to the 6 modulo 7, that's indeed 1 modulo 7. So we have verified that R equal to 6 is indeed the period for this particular calculation. Okay. We can do another. Suppose we ran the quantum circuit again, we might get a different answer. Let's say we got the answer for S over R as 0.10000. And let's say we got that answer instead. That's equally probable because it's one of the eigenvectors for this problem. Okay. Well, that binary expansion is simply 0.5, which of course is very straightforward. In continued fraction, it's just simply one number, 1 over 2. Okay. So therefore, here it's very simple to say, yes, S equal to 1, R equal to 2 is my guess for the period. R is equal to 2. Now we check 3 squared modulo 7. Well, that's 2 mod 7, which is not what I want because I want 1 modulo 7. So therefore, R equal to 2 is not a solution. So when I try the quantum computer in this way, I get only a guess, and the guess may be wrong. Okay, I get one of the guesses for the eigenvectors, and it's not always guaranteed that I'll get the right answer. So it's a question: have I achieved anything? And of course, to prove that the number of times that I have to repeat the circuit to get a good estimate for S over R is not a significant addition to the algorithm runtime, is a problem that obviously I'm not going to try and show you here in this class. Okay, that's for a more advanced course. Okay, there is proofs that you can go through once you understand how the algorithm works. But the point is that indeed it can be shown that it is not a significant overhead to the runtime of the algorithm. And in fact, what people showed is that the overall complexity of this algorithm is only order n cubed. So it's efficient in the number of bits for the problem. Okay. So that is a big step because, as I was saying to you, the period finding, we have no good classical algorithm at all. Okay. I mean, we have classical algorithms, but they are very slow. They are super polynomial in n. So this is a significant speed up. And as I said, the reason this problem is maybe a bit more important, and this is kind of one, is that this actually forms a subroutine in the other algorithm that I don't have time to talk to you about, which is Shor's algorithm. And that is the one that factors numbers. Okay, that is the subroutine that is at the heart of RSA encryption, which of course, RSA encryption is what we use for a lot of classical communication, secure communication. And if we can break RSA, that means that you can break most modern crypto systems that are used to, for example, exchange information with your bank, to send emails, visit websites securely, give you a credit card, etc. All of that is secured by a RSA encryption key. And according to Shor's algorithm, that can be efficiently broken with Shor's algorithm. One of the hardest part in Shor's algorithm is in fact the period finding. Okay, that's why I covered period finding. But Shor's algorithm has a few other steps beyond that. But I'm not going into those steps here. But because the main or the most rate limiting step is the period finding part of Shor's algorithm, that's why I talked about it here first. Because now we can use this in Shor's algorithm to actually do the factorizing of numbers. Okay, and your textbook has a pretty decent explanations of how RSA encryption works and how Shor's algorithm works. So I encourage you to read it, if you're interested in learning how Shor's algorithm works. Okay, any questions about this? Yeah, it's one of those algorithms that's very mathematical, and it's kind of hard to understand without going through it a couple of times. So I encourage you to go back and look over it. And of course, you can come talk to me. Oh, which reminds me, I just realized once again, I've forgotten to bring in your quiz 2 graded test. So if anybody wants your graded test back, please come and see me after the class and I can give it to you. Okay, I'm going to stop talking about algorithms and I'm going to move on to the next topic, which is quantum entanglement. All right, so this is just a pause here to see if anybody has questions about the algorithm. Yes.
So I guess just overview,
yeah,
the quiz on Friday, what kind of should we?
Yeah, you're not going to be asked to solve a period finding algorithm problem. Don't worry, that's too hard. Yeah. Is there any other question other than that? Okay. Yeah, I mean, all these algorithms, they are. You are expected to. Yes, go ahead.
Yeah, just about the encryption stuff. So if I remember correctly, for RSA encryption, the best we can do with the class computer is just a brute force solution, right?
Yeah, exactly. So it's called the number field sieve, basically. So you factorize numbers into their prime factors. You can show that you have to look, I think, square root of n number of factors, and then you have to basically try all of them one by one. And that's the only way to factorize. And of course, for n large, this is a very large number of things that you have to factorize. Yeah.
So to follow up on that, is the reason why RSA encryption still kind of works today is because what quantum computers aren't
Yeah, exactly. So for RSA 2048, which is the current recommended length of the key in RSA encryption, we would need, and the other problem is, I've talked about quantum computer that works here as a perfect quantum computer. So it's even if I had 2048 bits, I would need 2048 qubits, but it's not just any qubits. I need to run the full Shor's algorithm through them, right? The problem is none of the quantum computers are good enough yet to run the Shor's algorithm to that extent without errors. Secondly, it turns out that, you need what are called logical qubits. So this is one of the topics for the extra projects, which is quantum error correction, because all of the quantum computers, as we know, are subject to noise and decoherence, which you might see when you run some of your homework problems through the quantum computer, because you run the simulation, you get one answer, but you run it to the quantum processor, you may not get exactly that answer. You may get some histogram with errors, some of the values that you don't expect will show up. We actually saw that in one of the class examples also. So the histogram wasn't perfect, Well, you can imagine for a more complicated algorithm like Shor's algorithm, there's a lot more steps, a lot more gates, a lot more, each of these controlled U gates is itself a classical circuit that you have to implement with quantum gates. And so that's going to be extra errors. So all of this to be corrected requires something called error correcting codes in the quantum computer. and nobody has yet achieved like scalable operation of error correcting qubits in a quantum computer. That's the frontier right now. Like people are trying to implement error corrected qubits in quantum computers and scale it up to like thousands of qubits, thousands of so-called logical qubits as they're called. So there's a lot of research into this area. It's an active area of research.
I mean, quick question, how do they know that there is error?
They just run the algorithm and they don't get, answers even for like the right, for like small numbers of qubits.
Right, but like, how do they say, oh, this is error situation?
There's a lot of like calibration tests and things that you can do. You can run like, benchmarking, as it's called, where you have a set of gates. So like one of the things that, for example, IBM does is they run a set of like gates through the quantum computer for which, they're expecting a certain distribution of results. And if they don't get it, that's telling them that they have a certain level of error in the quantum.
So they are saying the quantum computer is error in a state, not every run through it.
Sorry?
So, for example, when you say direction of errors,
Yeah.
you're talking about at a quantum computer level, not at each run level. Yeah.
What's the difference?
So one run might be no errors.
Yeah.
Depending on
No, I mean it's like there's decoherence, which is unavoidable. So it means that that's like a feature of every quantum computer. Basically. Every quantum computer suffers from some kinds of unavoidable errors. So you have to correct for those errors automatically. So, yeah.
Yeah.
I mean, yes, I suppose there is a small probability that in one run, you may get no errors, right? But the probability is quite vanishing at some point, especially if you run thousands and thousands of games.
Yeah.
That probability is very, very unlikely, right? I mean, it's like if the probability of error is 99%, if the probability of your fidelity or whatever you call it is 99%, that seems like a small error, 1% on a gate. But if you run 100 gates, you're guaranteed to get an error on one of them, right? So that's the issue. Like,
Yeah.
and we typically for like a Shor's algorithm or quantum Fourier transform, you're running thousands of gates, maybe millions of gates.
I was just gonna ask, like, is the way to correct the errors while the run or after the run?
Yes, so they have to do that. They have to correct while you're running. You can't correct afterward because afterward means measurement, and after measurement, you're basically stuck. You've finished the run, basically. Okay, so I'm moving on to the next topic, which is quantum entanglement. So I'll just quickly remind you what quantum entanglement is. So many qubit states or 2-qubit quantum states can be factored into a tensor product of the individual qubit states. So for example, if I look at this state over here, 0, 0 minus 0, 1 plus 1, 0 minus 1, 1, I can factor that as plus state times the minus state. Okay. So in some sense, we can visualize these as 2 separate block spheres for each of the qubits. And in each block sphere, the qubit is in a well-defined state defined by a point on that block sphere. Okay. And so these are called separable or product states. But many 2-qubit states cannot be factored into a tensor product of individual qubit states. For example, the state 0, 0 plus 1, 1 cannot be written in this form. And we saw proofs of why this is true back when we did these examples. Okay. These states are called entangled states. Okay. Again, this is back from say week 7, that if I take some general 2-qubit state such as this, right, 1 over root 2 0 0 plus 0 1 plus blah 1 0 plus 1 1. Now let's say I ask you what's the probability to measure 0? How would I go about finding it? Can anyone tell me what's the probability of measuring 0 on the left qubit? Yes.
You square the amplitudes equation.
Exactly. So I square the amplitudes of the first 2 terms because those are the only 2 in which the left qubit is 0. So that probability is 3/4. Okay. And then once I measure that it's 3/4, that means that I'm left behind. Once I measure that it's probability that the left qubit is in the state 0, the remaining qubit must be in a superposition of these 2 states. And the amount of superposition is just obtained by dividing by square root of this probability. Meaning I take that state 1 over root 2 0 0 plus 1 half 0 1 and I normalize it. And the normalization constant turns out to be 1 over square root of 3 over 4. So I get this state over here. So this is an example of an entangled state which is not maximally entangled because after measurement of one state of one qubit, the other qubit is left in a superposition. So the measurement of the next qubit is still uncertain because I could get either 0 or 1 on the right qubit, okay, with some probability 2/3 and 1/3 in this case. But this is still an entangled state. It's a partially entangled state. But the I'll show you in just a minute the maximally entangled state, which are the Bell states, we have talked about them before, are the ones for which, for example, in this case, this is one of the Bell states, 0 0 plus 1 1. You can see if I measure the first qubit to be in the state 0, I'm guaranteed that the second qubit is in only one possible state, which is also 0. Yeah. Or if it's 1, then the other one is also in the state 1. Okay. So and we have seen how to create that entangled state, for example, by using a C0 gate. So I start with one of the states in a plus state and the other one in the 0. This is a completely separable state because it can be written as a product of the two states. But by acting with the C0 gate, I end up with one of these states which is not separable, which is an entangled state. And in fact, in this case, it's maximally entangled. And if I start with any one of these other superpositions and create the C0 gate, I get these other states, which are given the names phi plus, phi minus, psi plus, and psi minus, and they're called the Bell or EPR states. And I'll say why in just a minute. Okay, so this is all just a review of things that hopefully you're all quite comfortable with by now. Okay, there's one other thing that I didn't explain to you before, but I'll show it to you now. We can show that such states are entangled in any basis that you choose to measure them. Okay? What I mean by this is that the phi plus state, for example, which I wrote as 0 0 plus 1 1, can also be written as plus 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 minus minus. Or more generally, can be written as UU plus VV, where U and V are orthonormal basis sets or orthonormal bases. Okay, so here I'll prove that result to you, which is, I think, very unique situation with entangled, maximally entangled states. So I write a new basis set, U and V, okay? And U is a state, let's say A0 plus B1. Well, then because V is orthogonal to U and also has to be normalized, you can immediately show that V must be in this one. Okay, so it must be minus B0 plus A1. You can verify for yourself that if I take the inner product, VU, right, I'll get 0 and 0 will give me minus AB, and this one will give me plus AB, and that must give me 0. And of course, I'm demanding that A squared plus B squared is 1. Okay, that's also true. So this is an orthogonal basis set. Therefore, now I calculate UU plus VV. Okay, so this is just substituting A0 plus B1 times A0 plus B1 plus minus B0 plus A1 times minus B0 plus A1. Okay, so that is our state, and now we'll show that this is exactly equal to 0 0 plus 1. Oh, sorry, I should have written 1 over. That is still, I still need that 1 over. Okay, so now I just need to take all the terms. So this is in the first, I get a squared 0, 0 plus ab 0, 1 plus ba 1, 0 plus b squared 1, 1. And I'm just ignoring the 1 over root 2's, just assume they're outside. Plus, now on this side, I get b squared 0, 0 minus ba 0, 1 minus ab 1, 0 plus a squared 1, 1. And so you can immediately see this AB and this AB cancel. I mean, this 0, 1 and this 0, 1 combination and this 0, 1 and this 0, 1 combination cancel with each other. And so I'm left with and this, of course, is just 1, sorry, a squared plus b squared, b squared. That is just 1 by normalization. So I'm left with 1 over root 2 of 0, 0 plus 1, 1. So the maximally entangled bell pair, and this you can prove for any of the other maximally entangled bell states, is entangled in any basis, orthogonal basis that you choose to write it in, which is actually a pretty interesting result. It's not immediately obvious to me that that is true, but it turns out to be true. Good. So why is this all so interesting or confusing at times? So Einstein wrote to Max Born back in the beginning days of quantum theory. And the reason he was so puzzled and upset was due to this entanglement that we were just talking about. Okay? He felt that God, cannot be throwing dice and deciding which of these states is measured in any given experiment. Okay, so let's talk about that a little bit. So, as we just saw, the result of measurement on any one qubit perfectly predicts the result of the measurement on the second qubit. So, if I measure 0 and I know that I started with an entangled state, then I know for sure that the other qubit must also be in the state 0. Or 1, then I know it's for sure 1. And in particular, as we just said, this prediction holds no matter which orthonormal basis set you use. So this is what we call quantum correlation. It's like this. I give an example, which hopefully will make this a little bit more clear. Suppose suppose two people, Alice and Bob is a classic A and B for quantum physics. The Alice and Bob have an entangled state, or they can have two balls, okay? And the balls are either black or white, okay? They put the black and white balls into a box, okay? And they shake it around so they don't know. And then they put a divider in the middle of the box. And let's assume for now that the shaking and everything results such that each of them has at least one of the balls, okay? They cut the box into two, they don't look in it, inside it, and Alice gets on a ship and goes to Proxima B, okay? So at this point, Alice opens the box and she finds, oh, I have a black ball. Therefore, I know, okay, that Bob must have the white ball. And similarly, Bob, looking in his box, knows if he has a white ball, that Alice must have a black ball. This is collapse. In the statistical classical sense, we have collapsed the sort of uncertainty by measurement. Okay, but it's a very silly collapse because, everything was set up in advance. The balls, were exactly known to be black or white and so on and so forth. But what's interesting about quantum correlation is now imagine that when Alice opens the box, she doesn't look at the box with, regular black or white. She looks in some other color range, let's say red, okay? Imagine that, for example, that she's wearing rose-colored glasses when she's looking at the box. Well, what this quantum correlation is saying is, suppose she measures in this rose-colored glass frame of mine, she measures the ball is rose-colored, then she knows immediately that it must be anti-rose colored for Bob as well, no matter whether he chooses to measure in the black or white basis. Now, in fact, in quantum correlation, because the anti-rose, so to speak, might be equal superposition of black or white, there's a chance that, on the other end, if Bob doesn't measure with rose, but he measures with black or white glasses, then he's going to get an equal superposition possibility that it could be either black or white, even though originally the two particles were set up as classical balls. If they're quantum balls now, this possibility exists because of quantum correlations, which is different than classical correlations, right? There's no way that she can measure anything else in regular correlations that it's anything different, okay? So if we assume that the color of the ball or the properties of the qubit have a value prior to measurement or independent of measurement, we call that realism. Okay, it means we think of objects as having a property even before we measure them. Okay, this is how we think about the world, right? For example, if I ask you, what is the, if I ask you, okay, if a tree falls in the forest and there's nobody to hear it, do you believe that there's a sound? Do you believe there's a sound? Anyone? Yes, right? Or if you think about a leaf of a tree that's somewhere in some forest on the other side of the planet, assuming, this is a regular tree in the springtime, whatever, make all this connection, you can predict to a fair degree of certainty, you're assured that leaf of that tree is going to be green, right? Because we know a lot of things about things that we don't immediately measure or look at, even though they're far away from us, okay? So we expect that the property of this, the greenness of the leaf is going to hold independent of whether we measure it or not, okay? And the same can be said for almost any classical phenomenon. We expect even when we're not looking at it, the sun is still there and it's still shining on the planet, right? So that's what we mean when we say realism. We are thinking that properties have some reality independent of us measuring them, okay? And certainly, there's lots of things that we can think of as measuring devices. It doesn't have to be a conscious observer. If the tree falls in the forest, then for sure it's perturbing the sound waves. It's sending out sound waves. Those sound waves are perturbing, some of the atoms in some in the leaves of other trees. It may be heard in the eardrums of some forest creature, whatever, and that is then recorded as a signal in the brain of that creature. So that also is a measurement, okay? So we know that, for example, that those are all constituted as measurements, okay? It doesn't have to be a conscious observer, for example, okay? So, and we also assume typically that a particle being measured cannot influence the other particle's measurement faster than the speed of light. This is what we call locality. Again, that example, like, if there's a tree now on Proxima B, that we think, has the same conditions as us, for example, let's assume, then we think, okay, that's also probably going to be green. Let's say, I don't know, maybe it's purple, but whatever. So these perfect correlations, no matter how far apart the qubits are, has deep implications, okay? So again, this is just the example that I was just telling you about. Alice and Bob have one part of an EPR pair, and they go far away to distant corners of the galaxy. And so EPR comes from the thing, Einstein, Podolsky, and Rosen. They wrote a paper in the 1920s, which argued that basically because Alice's measurement was able to influence Bob's measurement faster than light, because we know as soon as Alice measures the qubit and gets the state 0, we know Bob's qubit must be 0. So this seems to indicate that there's some influence that propagates from Alice to Bob faster than the speed of light, because the Bob can be somewhere very far away, and we know immediately that this is indeed the case, that Bob's qubit outcome, measurement outcome must be determined by us. Okay, but this, of course, assumes that this holds even if Bob does not perform the measurement, right? That's what Einstein's thought was, so that is, okay. So the outcome of this paper at the time was it was just a paradox. The paradox being that, quantum mechanics was predicting that one of these outcomes should happen, but there was no way to really understand, whether that could be true in a theory that they thought every theory should satisfy what is called locality and realistic, which is just like that example I told you about Alice and Bob sharing a box. They came together, they interacted in a local, realistic way, right? They decided that, the box will have white and black ball, and they divided up the boxes and they took it away with each other. That's a local realistic model of what an interaction between Alice and Bob would look like. Okay, and then they go away, and because they get a certain result, they know that that result would have been true, right? Even if they were close by or whether they were far away. That's a classical correlation. But now we are saying this is true no matter what measurements they choose to perform on their qubits, whether it's plus or minus. We know that the result will always be plus or minus on the other side. So this was just a paradox. They said, there must be some other variables that control the result of these measurements. That is, there must be some list of things or variables that are imprinted in the balls beyond what quantum theory is saying, imprinted on the qubits, that the qubits know about. They have this list of things that they refer to. There's some variables, hidden variables, as they call them. And these hidden variables tell them, that they should give out this answer if this particular question is asked. Certain experiment is done. Okay, and that is all decided beforehand, just like in the case of Alice and Bob meeting first and getting the white and the black ball. Imagine now that when Alice and Bob met, the balls interacted with each other in such a way that they knew, okay, if she looks with rose-colored glass, make sure you give this answer and I'll give this answer. Or if she looks with, green-colored glasses, make sure you give this answer and I'll give this answer. So this is how the balls might have talked to each other when they were interacting inside the box. And then when you divided them up and took them away, no matter what experiment you did on them, they'll give you an answer that is decided by this list of all possible experiments and their outcomes. Okay, so that's what a local realistic theory is claiming would have to look like to give you these answers. Okay? So as I said, for 40 years, nobody really could go beyond this. They did not understand how to, because let's say that somebody did the experiment at the time that EPR proposed their famous experiment, nobody could do those experiments. Okay? But let's say even they had done the experiment, all one could have said is, well, okay, if the prediction is according to quantum mechanics, it's fine, but it just means quantum mechanics is still incomplete. There's some hidden variable theory that could explain the result and it goes beyond quantum mechanics. And you haven't shown me that your experiment in some way rules out these hidden variable theories. So that was the problem. But even if you had done the experiment and shown quantum mechanics was correct, well, EPR never said quantum mechanics was incorrect. They just said it was incomplete, that it did not have all of the information encoded in the theory to explain the result of the experiments. That was given by some local hidden variable theory. Okay. Well, so in 1964, John Bell showed predictions of any local hidden variable theory and quantum mechanics must diverge, must contradict each other. So, and that's exactly what he did. He allowed every possible experiment. So those two balls interacting, they can take on any experiment and they know the answer, encoded in some set of, variables that they know the answer to. And he showed that in spite of that, once the particles separate and can no longer communicate, let's assume that the hidden variable determines the outcome of the experiment. He calculated the statistics. He showed, I'm just giving an overview, I'm not proving those theorems here. He calculated the statistics for the experiment and showed all the local realistic theories obey a certain inequality, which is called the Bell inequality, and that quantum entangled states will violate the inequality. So now it's a matter of experiment. Okay, so he has put it in such a way that any local realistic theory must satisfy a certain inequality for those measurements that you make on the particles. And if you do the experiment and you find that your experimental results violate the inequality, you've ruled out all local realistic theories. Does that make sense to everyone? Why these Bell inequalities are kind of useful? So now it's left to experiments. Go ahead and actually do it. And that's what has happened over the years. So for example, recently, I forget which year, but Alain Aspect got the Nobel Prize for experiments he did back in the 80s and 90s, which in fact verified that Bell's inequality is violated. Okay? And more recently, there were still some doubts about his experiment, like he did the experiments and he put, like you need to make sure that the two objects can't communicate with each other. So you need to do the experiment. So of course, we can't go to Proxima B and do the experiments. But if you put the experiment sufficiently far away and then you randomly make the measurements so fast that the influence cannot propagate from one end of the room to the other, then okay, you're good, right? You can do the experiments in that way, and that allows you to rule out certain things. But there were still some doubts. There are other loopholes, so to speak, in these tests, which have now recently been closed. Okay, so in these sets of experiments from these groups, they have shown that even those loopholes can be closed, and now we completely think that nature is described by definitely not described, let's put it that way, by a local realistic theory, because the Bell's inequality has been violated for all of these experiments. Okay, so the question, of course, is all we have said is that Bell's theorem and experiments show local realistic theories do not agree with nature. So we have to drop one of the assumptions, either localism or realism. We have to drop one. That's what it's saying. Okay. Which one do we drop? That's the question that you can ask. So Niels Bohr proposed that he dropped the realism part, which is that quantum states are superpositions. They do not have actual values. They do not have real values until the measurement, and then a collapse occurs, which is what we've been sort of talking about. Like when we talked about like measurements and so on in this course, this is the interpretation of quantum mechanics that we have been following. Okay. That there is a collapse of the qubit when it's measured, and it gives you one of the output states that is in line with one of the states in the superposition. But until then, we can't talk about what the state of the particle is. Bohm proposed a theory where the realism part remains, but the hidden variables can communicate non-locally. Okay, so they somehow can communicate faster than the speed of light. Everett proposed the so-called many-world interpretation. In this one, both localism and realism are both satisfied, but he assumes that at every measurement, the universe splits into two branches for qubits, right? So 0 and 1. In one branch of the universe, the 0 is observed, the other branch, 1 is observed. Everything is completely deterministic in that particular universe. And Susskind and Maldacena proposed that something called ER equals EPR, as it is called, which says that EPR particles are connected by wormholes in space-time. So you may have, I'm sure all of you have seen movies where they talk about wormholes. So these wormholes were originally proposed as so-called Einstein-Rosen bridges in space-time. So it means that a particle here and a particle there, although they look to our eyes as though they are so far away that light cannot communicate cannot communicate between them in the time that the experiment is done, that in reality, the entanglement creates a tunneling through the space-time, and that tunneling through the space-time allows communication faster than the speed of light. So in reality, these two particles are sort of like, if you're on a paper, sheet of paper like this, right? And here's particle 1 and here's particle 2. They're somehow folded to come back and meet with each other. So here's particle 1, here's particle 2, and somehow the space-time has been folded in this way to like make them look like they are right next to each other. So there's no violation, no distance. Exactly, correct. Okay, so all right, so I'll stop here for today because we have run out of time. But basically, this is where we are currently in our understanding of like what quantum entanglement means and what Bell's inequality or Bell's theorem says about nature. Okay, I'm going to stop here.